Hi everyone, my name is Amy Hatfield, and in collaboration with Dr. Badawi, we have written a paper titled Moore's Law, What Comes Next? And we are from New Mexico State University, Klipsch School of Electrical and Computer Engineering. So, talking about Moore's Law, what's going to happen next? So, this paper essentially examines the incredible prediction that Moore's Law made in 1965 in his paper titled The Future of Integrated Circuits. And of course, the traditional definition, as many of you are aware, is that the number of transistors on a chip will double every 2 years. And there are many different works that have looked into this, and this one is an attempt at a modern look at Moore's Law and its derivatives, given the United States' new push for homegrown semiconductor industry. And there leads the question of, is Moore's Law still alive? There are many that think that it is or it isn't. And Intel is one of those that believes that it is still alive. And they recently put out this data that shows the tradition of Moore's Law over time and how it has continually increased as Gordon Moore predicted. And then what I've noticed is that there is a bit of a flattening around the year 2017. And I've pointed it out here on their chart. And then they make some predictions that's shown there in the circle. And of course, they do need to make the very needed prediction, which is there down in the bottom, as they have done, that future transistor counts are projections and are inherently uncertain. So it's just a quick disclaimer that, this could potentially not happen. But they state that it is going to, or they are going to try their best. So this leads to NVIDIA, who has declared Moore's Law done, no more. They instead have redirected attention to from CPU performance originally to GPU performance. And this computing performance is this new era that they're calling Huang's Law, and it's potentially what could be next for Moore's Law is this new definition titled Huang's Law. So there is a significant increase in GPU computing performance over the years, and this is what they are now redefining for Moore's Law. And there's that data, and there's also some data that shows an exponential trend for things like critical dimension. So if you want to say that Moore's Law should be defined using critical dimension, then there is a exponential decrease in that critical dimension size. So in around 1970, we were using about a 10 micrometer critical dimension size, and in about 2020, we were seeing a critical dimension of about 10 nanometers. And some of my research also showed that it's gotten down to 7 nanometers, even 5 in some cases. So if you do decide that you want to use this definition of Moore's Law, it's very much alive and it's not slowing down. So that could be one definition. And that leads into my next topic of discussion, which is defining and redefining Moore's Law. So first, let's understand that the driving force behind Gordon Moore's original definition was increasing complexity of electronic functions in a restricted space and minimizing the total weight. So that was the original driver. So think about that while we are discussing. And so this definition and these drivers have been studied over the years, and we've developed the National Technology Roadmap for Semiconductors, our NTRS, and that changed to eventually the International Technology Roadmap for Semiconductors, or the ITRS, and then eventually to the IRDS, or the International Roadmap for Devices and Systems. And there are a lot of publications on there that talk about the various challenges as well as various successes in the industry. And a lot of what I've been reading in the more recent publications is that there seem to be a lot of challenges coming out that we as engineers and innovators need to overcome. So in terms of redefining Moore's law, what does this mean? So we can take trends in various data and use that as our definition to keep Moore's law going. So in this data shown here on this plot, the orange shows the original definition of Moore's law. This is from Olivier Zrady's paper titled, "Is There a Moore's Law for Quantum Computing?" And there are 4 other microprocessor characteristics shown there that show a flattening. So that's for single thread performance, frequency, typical power, and number of logical cores. And each of those eventually shows a flattening, which leads me to believe that Moore's law is destined for that it's going to. And it cuts off the data right around where I would say we do start actually seeing that flattening that would match up with Intel's data shown on the last slide. So that's where we reached these other definitions of Moore's law. You could say that there was a Moore's law for a short period of time for the single thread performance, let's say. And this is because Moore's law is not a traditional law. It's not like a law of physics. It can change. And because it can change, we can keep defining it to keep it alive. And there are many ways that we as engineers and scientists and innovators have kept it alive. And there are a couple of ways that we have done that, and I'm going to talk about a couple of those here. There are cooling methods, lithography methods, wafer size evolution, and material changes that have kept Moore's law going. And to talk about just a few of the cooling methods that are state-of-the-art, the first one is solid-state refrigeration. This one involves passing electrons through some barrier between the emitter and the collector, causing cooling at the barrier. And there's a lot of advantages to this type of cooling method, but it's really, really complex and difficult to manufacture. So that's one of the drawbacks of solid-state refrigeration. Then we also have thermoelectric cooling. This involves passing a current through 2 different metals or semiconductors connected by a Peltier junction. And this one is very well understood. We have a lot of manufacturing flexibility with this one, but there are a couple of issues with the heat dissipation where you need to really understand exactly where that heat is going to be dissipated in order for this one to work. So next we also have thermoionic or thermotunneling. This is where you carefully evaporate the emission of hot electrons across a wall, along with a vacuum gap from cathode to anode. So there's a lot of theory that goes along with this one, and there is no resistance that needs to be accounted for. So there's only one mode of heat transfer here, which is radiation. So this method isn't really very easy to implement. And the use of these is limited to practical devices. So in my opinion, the thermoelectric cooling seems to be the most promising one that we can continue to use to and develop to keep Moore's law going. And next, I want to touch on wafer lithography. So particularly EUV lithography has been one of the latest and greatest developments for lithography methods. That's extreme ultraviolet lithography, and that ultraviolet light combined with a larger numerical aperture size can improve the resolution of the pattern that you're etching into your wafer. So then we can increase, or improve our critical dimension, and that could keep that definition of Moore's law going. And then next we have wafer size. So wafer size has also shown a trend over time, where we started out here in the table with 1-inch wafers in the 1960s, and we've gone all the way to develop 18-inch wafers, though typically we use the 8-inch or the 12-inch just due to manufacturing capabilities, though I do know that there are some places that produce the 18-inch as well. And then fourthly, there are some material changes that have kept Moore's law going and that could potentially keep it going in the future. So graphene is a really promising material. This is because a graphene insulator semiconductor is better at determining whole photocurrent that comes from the semiconductor substrate, because the graphene has a low light absorption, whereas a metal insulator semiconductor has that high light absorption, and that makes it more challenging to make those photocurrent measurements. And so that's not to say that graphene is the only option here. It's just an example of one of the promising materials that could keep Moore's law going in the future. And not only that, but these are ways that we've kept it alive, but there are also some challenges that Moore's law has faced over the years, and that includes economics. That is because economics can potentially slow the evolution of Moore's law. And this is because when we have money for research and development, we can therefore create new products and innovations, and then we can create new revenue through these new products, which we can then put back into the research and development. And it is just this never-ending cycle of money with the research and development. So if there is a slump potentially in a lot of research and development, then there aren't going to be new products to create new revenue, which can be a really big problem for the industry. And one of the promising things that is happening now in the United States semiconductor industry is the CHIPS Act for Digital Twins and the Semiconductor Chips Manufacturing Institute that is going to be started here in the United States. And this was stated by the U.S. Department of Commerce in early May of 2024, so just a couple months ago. and it's a $285 million project to help with the semiconductor industry in the United States. So the Institute is going to basically create these virtual models with the same structure, context, behavior as actual chips. And this is going to create new jobs, it's going to increase innovation, and it's going to reduce the cost of research and development. So we can potentially move Moore's Law and the semiconductor industry forward even more. So that's a really promising thing for the US semiconductor industry. And then there are some more future prospects for defining a Moore's Law, which is quantum computing. And in quantum computing, there are trends that are present for things like qubit numbers, qubit fidelities, or others. And this quantum computing is a highly cross-disciplinary field, so it's very different from the original Moore's Law, which was very straightforward and only applied to integrated circuits. And there are many different types of qubit technologies that are very diverse in terms of physical aspects. So we could have various definitions of Moore's Law for quantum computing. And this plot here comes from Olivier Ezrati's paper. This data comes from D-Wave, IBM, Google, Rigetti, and there is a consistent increase in number of qubits over time. And the only one that you could argue that there's not a very distinct trend would be the Google line or the green line on the plot there. But there is still an increase nevertheless. So I do think it is a little bit too early to be defining a version of Moore's Law for quantum computing and really strictly defining that yet. But as the industry for quantum computing sort of breaks through, I think we can develop one pretty shortly. So that leads me into my conclusions, where we have been keeping Moore's Law going over time. We as engineers and innovators are doing it through things like cooling methods, lithography, material changes, wafer size, and there are also other areas of technology where Moore's Law could potentially be defined, like quantum computing and also critical dimension. I think with the Moore's Law definition for critical dimension, it's too soon to determine that this one is the end. So the ultimate moral of the story is that new definitions of Moore's Law are going to continue to develop in this never-ending cycle of redefinitions and patterns and identifying trends in various areas of technology. So Moore's Law is still kicking, and it's going to continue to be redefined. Thank you.